Hello everyone, my name's Randall and I'll be continuing our MATLAB workshop. This is the very last part that we're going to do for now just because we want to get a better understanding of Simulink, and that is what I'm going to be showing right now. Now I do have a minimal amount of experience, but I can show you what I know. So we're going to start this with a passive high-pass filter. Basically, we could take a look at this circuit we have in front of us. You can see that there's a capacitor, and that's only allowing high frequencies to pass through. So if we look at it more in the frequency domain, we can realize that x of t is equivalent to x of s, y of t is equivalent to y of s, and then we can look at our capacitor as an impedance rather than just a normal capacitance. This allows us to treat it like a resistor, and then we can solve it how we would normally would. So I like to do this. This is pretty easy with nodal. So our first current, which would go through the resistor and the capacitor, the first resistor, what we could realize is, well, on this side, we have x of s. This side, we have y of s. X of s minus y of s, that would give us the voltage difference. And then if we divide it by our resistance, which would be R1 plus the impedance of the capacitor, that is equal to the current that we just wanted to find. Now, that current should also be equal to the current right there. So y of s, well, down here we're treating more as our ground. So y of s minus 0, I'm not going to put that, over R2, that'll be the same current. Now, if you don't know the impedance of the capacitor, you could solve for it with calculus, or you could just realize, okay, well, we could also just say it's 1 over SC because that's equivalent. So now I'm not going to solve that. I don't really need to. If you wanted to solve it, all you have to do is get it in terms of y of s over x of s, because that will give us our transfer function. So we already have our transfer function. Our transfer function is s over 2s plus 1. You could rewrite that if you'd like. It doesn't really matter. You could rewrite it as 1 over 2s over s plus 1 over 2. That format's a little bit better just because you can see that there's a magnitude of 1 over 2, or a gain of 1 over 2. So now we want to put this in different terms just so that we can basically put it into Simulink. So this is how we want to draw it out for something in Simulink. This might look very confusing, but basically what's going on is we have an input into a system, and then we have an output into the system over here. This 1 over s term, that is what we call an integrator, and if you don't know what that is, it's basically if you take the frequency transform of or if you take the frequency transform, or the Laplace transform, or the Fourier's transform, then you can get, or if you take that of an integral, you get 1 over s. So now, this still probably looks confusing. Here, I'm going to put it in this format, and I'll explain what it is as I go. So basically, how we want to do that, how we want to get into that format is we want to realize this relationship into our function that we have. So let's say I'm not going to use h of s. I'm going to use y of s over x of s is equal to, you can put the 1/2 s over s plus 1 over 2. You don't need that 1/2 in front. You could have left it like that, but it'll help us in the long run. So what I like to do to get us started with, I like to get y of s on the left and x of s on the right, or vice versa. So I'm going to multiply the denominator on the right side over, so s plus 1 over 2. And then I'm going to leave the 1/2 on the right side, so I'll get x of s, and I'll have s over 2. So if you noticed, when we were looking at this format over here, we only have 1 over s. We don't have regular multiplied by s. So I don't like this format. What I'm going to do is I'm going to divide everything by s. So I'll have y of s 1 plus 1 over 2s, or I'm gonna go, yeah, I don't want to do this, but I'm going to input 2s is equal to x of s, and then 1 over 2s, and those two are equivalent. So now, what I want to do is I actually want to get our output by itself, because if I were to FOIL this, so y of s times 1, and then y of s times 1 over 2s, the 1 over s creates basically a delay, and we don't want that. We don't want the delay in our answer, we want just the output in our answer. So what we're going to do, let me finish writing this top part out. So what we're going to do is we're going to move it over to the other side. So we're going to have x of s times 1 over 2s minus, because we're subtracting over the delay for the output, and then 1 over 2s. So basically, if we want to interpret this, we have our output. That 1 over 2s, that's actually a delay in the input as well, but we're still going to be looking at just the input. And then this is basically feedback. So let's take a look at this picture again. I'm sorry if I'm going around fast. But so we have our output. If you want to interpret this, this is kind of our feedback right here. And then this is the delayed of the input. This little arrow right here, this is just a normal input being added in. So x of s, just normal. But then right here is an x of s times 1 over s. So let's try to draw that. But in terms of our equation right here, y of s is equal to x of s times 1 over 2s minus y of s over 1 over 2s, yada yada. So let me use a different color. X of s, so we have our input into the system. Well, so now first thing I need to think of is, or I like to draw it out like how it is above. And we don't, normally you could have another 1 over s down here, but we only have 1 over s. What this is doing is this is kind of the equivalent of saying, 1 over s squared. We don't have any 1 over s squared terms over here, so I'm not even going to worry about bringing that down another. Also, we don't have a normal x of s being added, so this, you could put 0 or you could just get rid of it. So now, I like to put an arrow. The reason why you have the summations all over the place is because if you have terms down here, then you want to be adding it as it goes up so that everything's connected. Because if you're just shoving 2 wires into something, that's not always the best thing. So I'm going to go ahead and put the summation symbol, and then a summation symbol, even though those aren't even needed. And then now we need to think, okay, well, our input, we have that 1 over s being multiplied, but we also need a 1 over 2. So now this is continuing the format we have. So now we have an output, so y of s, and we don't have our feedback yet. So what we want to do is we want to bring down 1 over s. That'll create feedback. And then we want, there's a negative 1 over 2 term, summation, and then over there. Now, here's the thing, you could simplify that a lot. Honestly, you don't need, I'm going to change colors, you don't need that, or even that, but I just left it there to show you formatting. You don't need 2 arrows there. You can honestly bring this whole thing up if you'd like, but you don't even need to do it. It doesn't matter. The reason why I left it like this is because this is just a starting position for any of them that you're going to be doing. So I could simplify it where I could have x of s, and I could have 1 over s, and then I could just have 1/2, and then I could have a summation, and I could have y of s, and then I could have 1 over s, and I don't even need I could just go straight up there and -1/2. That's fine, you could do that. I'm not going to because for teaching purposes. So you could do that, that's one way, or you can do it this way. You could do another way of simplifying it. You could look at this and you can kind of make a difference. So there's this side and this side, right? Well, what if I told you you can move things around? What if I told you you only need one integrator? So now what you could do is you could carry it down and you could say, hey, x of s, and we don't have the normal x of s going in. So what we do is we kind of rearrange it to where we flip sides. This might be hard to see, but basically what I'm going to do is I'm going to put it in like this, summation. This would normally be x of s, the normal x of s being added over. But we're not doing that now. What we're doing instead is we're going to be dropping it. It's going to have 1/s. And then this, ooh, that's a crappy arrow. This is our -1/2. This is the y of s, 1/s. That's what's going in right there. So I'm literally taking this whole right side and putting it on the left. So now we put a summation, go up. You might want another summation there, but that's up to you. You don't need it. It's not very clean. The reason why I'm doing the summations again is because if we have more things on down there, then we want more summations so that everything's being added together. So then now we need to put in our x times 1/s, which is this guy. This is the x of s, 1/s. So we need to multiply that by 1/2, the sum. You don't need the sum, but if you have a normal x of s, then you're going to want that, but we don't. And then if you have more stuff going up, you know, it'd be helpful. So now this is still our y of s. You might look at that and think, oh gosh, that's not the same thing. That doesn't even look like the same thing. Well, it is. I believe it's actually called the direct form 2, or df2. If we were to simplify this top one, that would be df1. You know, whatever works for you, because honestly, if you like this better, stick with that. I'll go ahead, I'm going to stick with that when I use it in Simulink. So let's go ahead and take it to Simulink. We're going to lose this in a second when I click on the screen, but so we're in Simulink. How do we get started? I like to go in the library. We're going to need some stuff. Believe it or not, all these components are in the library. We have x of s and input. That's not going to be in there, but you're going to need to find some kind of source. We're going to have an integrator. We're going to have something that allows us to sum, and we're going to have a gain operator as well. So let's go into the library and find what's in there. Loading, loading. There we go. First thing I like to do, commonly use blocks. Hey, there's a gain operator. Grab it, drag it. I only need one. How fast is it going to load? You can see the integrator. We're also going to need the scope, because the scope, it basically will act like an oscilloscope, letting us probe into a circuit. All right, let's go back in the library. Running OBS and running MATLAB and everything, it really slows my computer down. So we're going to need the scope, because that's our oscilloscope. We're going to need an integrator, like we had in that direct form 1 and 2. So all of these items that are in the commonly used blocks, they're going to be throughout this entire list here. The first thing I would do is I would look in continuous, unless you're doing a discrete circuit or something with on some digital. So there's our integrator. We already found that. We could even use a transfer function, but I'm not going to do that. Okay, so that's not really what we want. We want sources. So constant, ramp, pulse generator. I'm going to use a sine wave to start, and then I think I'm going to go to a pulse generator just to show us some other stuff. Is this everything we need? Oh, no, we need one more thing. We need the summation. So let's go to our math operations. So we could use add. I don't really like using add. You could use a lot of different stuff. There's subtract. You could do some funky stuff to make subtract work. I like to use sum of elements. Makes it a little easier. All right, so let's take a look at our picture again. We're gonna have x of s, and then we're gonna have a 1 over s. I'm gonna format it just like this. We're not gonna need all these summations though. I think because only right here is the one spot that it sums two different signals. So let's go ahead and get started. First thing I'm gonna do is if you double click on these objects, you can it'll give you a full parameters for it. So you could go and click, okay, so 1 over 2 is our gain. Did it change? It doesn't look like it changed. I guess maybe I need to hit apply. Well, another thing you can do is you could actually just type in as well, right there. Okay, if you click on it and you hit Control R, you can rotate. I'm gonna go ahead and make another one because I know I'm gonna need another one. I'm going to go in here. Double click if it's not working out very well. We go over here. There we go. Negative. Apply. Okay. So then another thing is I'm going to rotate this, copy that, paste it. There we go. All right. So I guess I didn't need it up and down. Let's rotate it again. Rotate this guy again. There we go. I'm trying to mimic how it was in our picture. And then we had a summation right here. Because the reason why we do it in this format exactly is because all of the x terms is going to be on the left, all the y terms are going to be on the right. It's really easy to see everything because it's laid out well. So now the summation, this is actually our output right here. But because we're not actually plugging it into a circuit, that's all we have to do right there is just know that that's our output. So let's take the feedback from our output and we're going to feed it into our summation. That's kind of it. So again, if you want to make different parameters with all these, like here's our source. This is a sine wave, but if you wanted to change it to cosine, you could just double click it. Go in here, you can change the amplitude, you can change the frequency, the phase, and the phase is what you really want to change if you want to get a cosine. Okay, so right here, you can click right here, drag it over, that's our input. You could get another scope, or you could just hover right here, double click, now you have two. All right, so here's one thing is that if you want to change how long this scope is viewing things, you can click up here because 10 seconds might be fine for the sinusoidal wave or sinusoidal function. However, when I do the step function or square wave, then I don't want 10 seconds. I want to show more. So let's go ahead. I can click run, or I could just double click onto the scope. And I'm going to have to hit run anyways inside. So now right here, I hit run. You'll be able to see over here, let's say t equals 30. That's how long it's running. Give it a second. T equals 30. So, okay. It kind of looks jaggedy, and that's because it only has a certain amount of samples it's picking on. When we created our transfer function or messed with it, we knew that it was a high-pass filter with a gain of 1/2. If you look, that's what's happening. We are losing our signal by half. It is passing through. So if you were to change this time to 10 seconds, ooh, my computer's not slowing down on me. 10 seconds. Let's go into the scope. We're going to have to run it again. And you can see it should be a lot smoother. There we go. It's because there's a lot less range, and there's the same amount of data points. Okay, so that's all dandy. I'm going to go ahead and delete that though. And the reason is because I am going to add the square wave. Let's go to sources. Let's see, pulse generator. And the reason I want to do this is because we're going to stop thinking about it in terms of frequency. We're going to think about it in terms of just what we learned in circuits in the very beginning with the DC component. So now let's go ahead and double click on the scope again. Let's run it. We're going to see something a bit different. We should see exponentials to charge up the capacitor, because if we look, ooh, that's not great. Oh, I know why. So if you want to change up your pulses, you go into the pulse generator. It's because we didn't give it enough time to actually charge up. So right now the period is 10 seconds. That's fine, but I actually want our pulse width to be 10 seconds. So what I'm going to do is I'm going to do 20, so period is 20 seconds. But then the pulse is going to last 50% of that. So that means that it's going to be on for 10 seconds, off for 10 seconds, which is perfect. All right, and then let's go ahead and double click onto our Scopy. Run it. Now it should be on for 10, off for 10. So if you want to change, I believe we go to view, no. Well, we can click on this little settings. You can change the size. Oh, wait, no. I know what we need to do. We gotta change the stop time, because we didn't change it back. So 30 seconds, go into our scope, run it, it'll automatically adjust. You can manually adjust it if you don't want it to be automatic. Let me pull up the circuit. That's perfect, because what's happening is as soon as it turns on X of t, it'll be on, and then the capacitor is going to be taking its time to charge up. That's because we're adding, you know, as soon as we turn it on, it's going to be treated as a short, but it's going to, or not a short, and open, sorry. That charge is going to build up on that side of the capacitor, and it'll also cause it to build up on that side. So then as soon as we turn it off, it'll discharge. And if you've taken a basic circuits class or EM physics class, then you can kind of realize that this makes sense. Let's see, how much time have I used? Okay, let's see if I can do this real fast. Ooh, let's reopen this. Now, I told you that we could, that this is what we just did right here. Or no, that's, no. Yeah, kinda. This is what we just did right here. This is the original formatting that we used to build off of to make it into this one. And then with this, if you want to simplify it, this is direct form 2. Let's see, you know, I would definitely practice this, or if you have trouble, maybe email me and I can make another video just how to use DF2. But the reason why this is valuable is because we only need one of these integrators. So let's see, how are we going to do this? Actually, I could probably look at this picture right here and kind of use that. Sometimes I have issues when I copy an entire circuit like this, but I'm going to try it anyways. Okay, so we're going to have, yes, we're going to need a sum of elements, but we're not going to need them like how it is right now. Let's go ahead and delete. I believe actually what we're going to need, delete that. What we're going to actually need is we're going to need that there, that there. That's perfectly fine where it's at. Let's see if I can move this guy over. Delete that, move that. All right, I think that's basically everything. Because now what I can do, I could take this guy over here, this guy over here, this guy over here, and then this guy over here. Now, if we had the original x of s term, instead we have a delayed or integrated term. If we had the original, then it would be into a summation with this and then go into the Scopy, but we don't need that. I do need to go to the original. I don't like that. Yeah, there we go. All right, so this is our new one. Is it the same? Let's find out. So, taking a look at the picture, this is our original, which is down here. It should look very similar. So now what we did is, if you want to look at this compared to this, we combined those integrator terms in the middle here. We moved over both of these guys, and then because of the way it changed, basically we have our original x of s being added to all this right here. This is the feedback right now. So let's test it, see if it does the same thing. Click on the scope. We're going to need to hit run as soon as it opens. You could hit run up there, but I don't know. I'd rather just do it like this. While that's running, I can go ahead and I'll open up this guy as well. And moment of truth, they look the same. So I hope this video helped. I'd like to maybe make another Simulink video in the future, maybe find someone who knows it better than I do. If I were you, I would play around with this. I would use a different circuit than I did. Go into the library, look around. You can do a lot of digital logic design stuff in here as well. If you see things that I have that you don't, it's probably because I have maybe a library downloaded that you don't, or because at the Chico State campus they're offering it for free right now. I would take advantage of like the DSP toolboxes. I'm pretty sure those are added, or maybe the control systems toolbox, or there's a bunch that I don't have downloaded. So please try and have fun with that. Besides that, thank you for watching.